Thank you very much for the introduction and for the invitation to look at this workshop. So in this talk, I will introduce a branching particle system to investigate the internal mechanisms underlying FKPP fronts. But before introducing this model, I will start with some motivation from population genetics, population dynamics, and PD theory. So in this talk, I will be interested in population models that describe the invasion of one-dimensional environment by a cooperating population. What I mean by a cooperating population is the population that undergoes two opposite forces, competition for resources, as any biological population, and cooperation, which means that individuals cannot thrive without the help of their congeners, and that can model many different mechanisms. So my question is the following. In such population models, what are the microscopic mechanisms that drive the invasion? And is there a switch in these mechanisms as the strength of the cooperation increases? So, standard deterministic approach to tackle this problem is to consider an FKPP reaction diffusion equation that governs the density of individuals in the environment, that I will denote by U, where UTX is the density of individuals at location X at time T. So this reaction diffusion equation is like that. So you have a diffusion term that describes the migrations of your individual, and the reaction term, the orange one, that encode the local birth and death dynamics. And in this talk, I will focus on reaction term of this form. Maybe so this reaction term will be F view equals R view 1 minus U 1 plus VU. So if you only look at this part, you might recognize the classical FKPP nonlinearity that tells you that on each side you have logistic growth. So the growth is exponential until you reach 1. And so this term is some kind of saturation term that prevents the density from exceeding 1. And so it models the intraspecific competition. And here I will focus on the version of this reaction term where I multiply this logistic growth by a cooperation term. That's why we'll call this a cooperation term. So in this cooperation term, I have a positive dependency on the density U. And if I look at the per capita growth rate in this equation, that I will denote by R0 and define as f of U divided by U, then what I can show is that if B is smaller than 1, then R0 is maximum at 0, whereas if B is larger than 1, R0 is maximum at a density U0 that is positive. And in this case, I will say that there is cooperation in my PD. Why? You see that in the first case, to get the best per capita growth rate, the best strategy is to be completely isolated. Whereas in this case, it's better for you to be in a small group of individuals, which size is given by this U0. And you see on this plot that as B increases, U0 is shifted to the right, to 1, and so B will be the strength of the cooperation. So this is the deterministic model. The first question you can ask yourself is, what is the long-time behavior of this model? And a very important result for FKPP equations is the following. If you start the equation with an initial condition that is a step function, in which you say, okay, before this x0, the space is already occupied, and to the right it's uncolonized, then quite quickly your solution will converge to a traveling front solution that is a stable profile that I denoted by phi, moving at constant speed c. Okay, and the stable profile tells you exactly how the colonized region advances on the uncolonized one at constant speed c, and so the speed c will be interpreted as the speed of invasion. And so depending on this speed c, you can distinguish two classes of invasions. So if the speed c is the same as in the linearized equation at 0, we say that the invasion is pulled. And if it's faster than that, it can't be slow. If it's faster, we say that it's pushed. Why do we say that it's pulled in the first case? So you see that the speed only depends on the value of the reaction term at low densities, so at the tip of your front. And so we say that the invasion is pulled. And in the second case, the dependency on f is usually a bit more complex, and the whole nonlinearity can contribute to the speed. And in this case, we say that the invasion is pushed by the bulk. So for this reaction term, what you can show is that there is a critical value for the strength of cooperation, B, that is 2, such that below 2, the fronts speed 1, and the fronts are pulled, whereas for B larger than 2, the speed of invasion becomes an increasing function of B, and the fronts are pushed. So here we see a first transition in the macroscopic behavior of FKPP fronts. It suggests that there should also be a transition in the microscopic mechanisms of the invasion. Okay. Based on what I just said, it's quite natural to ask ourselves, where are the particles driving the invasion in these two regimes? Okay. And since the particle driving the invasions will be the same as the particles driving the evolutionary dynamics of the population, you can also phrase this question in terms of genealogies. Like if you sample 2 or more individuals, where will be located the most recent common ancestor of these individuals in the past? Yes? It's so I agree that this critical value is not the same as this one. So you can have cooperation, like there is a part of this regime in which you have cooperation, but the fronts are pulled. It's not enough, but maybe we'll, yeah, the cooperation is not large enough to be like, these two. I don't think there is a simple way. Okay. Okay. So we don't have particles yet. We'll see it in a minute. Yes, again, based on these this phase diagram, we would like to say, okay, in the pool regime, I conjecture that the individuals or the particles that lead the invasion are at the tip, whereas in the push regime, they should be in the bulk. But we can't conclude from that because there are no particles. And it turns out that it's also not so simple. And the first reason that is that there is actually not only two regimes for FKPP invasions, but three. So the FKPP equation, you can see it as the hydrodynamic limit of some class of individual-based models with particles, in which you let the local density tend to plus infinity. Here, the parameter giving the local density will be denoted by L. And so you can wonder, like, when you take this limit, what is the order of the fluctuations around the deterministic limit? Okay, so this was done in a paper by Birzu, Hallatschek and Korolev, in which they considered an individual-based model, took the limit, and looked at the fluctuations for the position of the fronts in this model. So they computed the variance in the position of the front and proved, observed numerically that it grows linearly with time, and that there are three regimes for the proportionality factor, sigma square. So for large values of the cooperation, namely p larger than 4, the variance k is like 1 over n, which is standard order for fluctuations to get a central limit theorem. But for b smaller than 4, you get much larger fluctuations. So for the pool regime, you get huge fluctuation in 1 over log n cube. And for b, like in a subclass of the push regime, for b between 2 and 4, you also get big fluctuations that are polynomial in n with some exponent, and that is between -1 and 0, and that only depends on the speed of invasion. And so this leads to the distinction of two classes of pushed fronts, and that we call semi-pushed and fully pushed fronts. Now the goal is to design a toy model that helps capture the internal mechanisms that lead to these fluctuations. Okay. So for now, it's only based on the fluctuations in the position of the front. So for fully pushed, you see that you have the fluctuations of the order 1 over n. Okay. You call it fully pushed, and if it's larger, you say it's semi-pushed. And we'll try to give a better definition of that. So let me introduce the model, and then I will explain why it's a model for traveling fronts. So I will consider a branching Brownian motion on a positive real line. Branching Brownian motion, it's particles that diffuse and branch independently. And independently is very important here. So I will assume that they branch at an inhomogeneous branching rate. That depends on the position of the particle, and I will call R of x. And in this case, it will be really simple. It will just be a step function that takes the value 1 out between 1 and plus infinity, and b divided by 2 for some small b larger than 1 between 0 and 1. To compensate the growth of my system, I will drift the particles to the left at a drift mu that depends on this parameter small b. That will be chosen so that in expectation, the size of the system stays approximately constant. And I will kill the particles when they reach 0. Killing boundary at 0. Okay, so now you might be wondering, why is that a model for FKPP France? So the idea is the following. So this model is a simplification of the dynamics of the particle located in a moving frame following the tip of the invasion. So in the red frame on the right. So in this moving frame, the density of particles is really small. So they should evolve independently, and the effect of competition is negligible. So they should experience exponential growth and again move independently. This is why I consider branching Brownian motion. Then my branching rate, so the step function, is an approximation of the R0 in the moving frame. Yes? Not exact. Yes. We'll see that it falls in the same unit. So we'll see that it does not depend on the entire profile. It depends on what happens to the right of the bulk, where the population density is of order 1, but not from what's happening to the left. And so the green line is simplification on the left of what's happening on the right in the moving frame. As I said, the frame is following the tip of the front, so it should be moving at speed c, and it will correspond to the drift in the branching Brownian motion, not in a moving frame anymore. And yes, I will use that a priori. The particles that are too far to the left, they won't contribute to the invasion anymore, so I will just remove them from the system by killing them at 0. This is the interpretation of the model. We can also show that it's a good candidate for a toy model because it exhibits the same macroscopic behavior as FKPP France. First, you can show that the drift mu exhibits the same kind of phase transition as the speed c of the France, in the sense that there is a critical value for small b, such that below this critical value is enough to put a drift constant equal to 1, but for b larger than b1, the drift has to be increasing with respect to small b. Maybe it was not super clear what I just said, but small b plays the same role as capital B on the right, because when you increase capital B on the right, you see that the height of the bump will increase. And so the small b in this model is the size of my step at the origin. So this will also play, this will play the role of the cooperation strength in the branching particle system. Okay, so we have the same behavior for the speed, and also we can show that the configuration of particles in the branching Brownian motion has the same decay as FKPP forms, in the sense that there is an exponential decay, and the exponent in the exponential depends on the drift through the same relation as the decay in the FKPP front depends on the speed of invasion. And so in this model, I will call this regime the pulled regime, and this regime the pushed regime. Okay, so from now on, I will focus on the pushed regime and try to distinguish the semi-pushed and fully pushed regime. So we saw that in the individual-based model studied by Birzu, Hallatschek and Korolev, they could make the difference between semi-pushed and fully pushed fronts by studying the fluctuations in the position in the front. Here we'll do the same, but we'll study the fluctuations in the size of the system. So I will denote by zt the size of my system at time t, and at time 0, I will start my system with n particles located at 1 to mimic like this step function in the particle system. And here n will play the same role as before. It's a demographic parameter that that is meant to be large. Okay. So the next step is to define an exponent in the exact same way as in the previous individual-based model, just replacing the speed of invasion by the drift in the BBM, and showing that there exists a second critical value for the cooperation in the branching particle system, such that between the two critical values, B1 and B2, this exponent is in 1, 2, as in the previous model. And this is what will delineate my semi-pushed regime. Okay, so now I can talk about the fluctuations. So I let the BBM, in the size of the BBM. So the first result is that between the two critical values, B1 and B2, the size of the system has a scaling limit on the time scale n to the alpha minus 1, and that the limiting object is given by an alpha stable continuous state branching process. So I won't describe this limiting object, but I want to emphasize that we find exactly the same time scale as in the other model. Okay, and then there is a typo. The second regime is the fully pushed regime. Okay, so this is my semi-pushed regime. And in the second regime, that is the fully pushed regime, I can show that B larger than the second critical value. I also have a scaling limit, but now on a different time scale, that is capital N, and that this scaling limit is given by a Feller diffusion. So I will now give you an idea of the proofs, because quite interesting, as the idea is to identify the particles that generate a fluctuation of order 1 in the scaling limit. So in the semi-pushed regime, you can show that the fluctuations in the limiting objects, so the alpha stable CSVP, are generated by excursions of particles far to the right at a distance log n of the killing boundary. And when these particles are drifted back to zero, since the growth is exponential, they will produce of order n descendants. And this will generate a jump in the scaling limit. And these excursions, you can see them on the timescale n to the alpha minus 1. And the reason why you get an alpha stable CSVP in the limit is because you can characterize the tail of the Erskine distribution of these particles, and you'll get an heavy tail in 1 over x to the alpha. And so in terms of fronts, what you want to say is that in semi-pushed regimes, you are in the pushed regimes, the speed of invasion is faster than in the pull regime, but the invasion is driven by excursions at the tip of your front. Okay, and in sharp contrast, in the fully pushed regime, like the drift is too strong, so you can't see excursions on a timescale that is shorter than n. And so all the particles, they stay in the vicinity of 0, and thus they have almost the same contribution to the process. And this is why these contributions, they just average out as in a central limit theorem. And so in this case, we say that the invasion is pushed by the growth in the bug. I will conclude by saying that I just showed you a particle system that falls into the same universality class of FKPP fronts, and that allowed us to capture what are the different in the internal mechanisms in the invasion between semi-pushed and fully pushed fronts.